I've received a question about this problem, which is 9.2.29 in the top right corner of the either study plan or homework, wherever you're working. So let me click View an Example. So we have a researcher wishes to estimate the average blood alcohol concentration, otherwise known as the BAC, for drivers involved in fatal accidents who are found to have positive BAC values. He randomly selects 1,300 such drivers in 2009 and determines the sample mean BAC to be 0.19 grams per, I believe that's deciliter, with a standard deviation of 0.09 grams per deciliter. Completes part A through D below. All right, so part A says a histogram of blood alcohol concentrations in fatal accidents shows that the BACs are highly skewed right, so very skewed right. Explain why a large sample is needed in order to construct a confidence interval. Well, that harkens back to chapter 9 or in chapter 8. So remember that either your distribution has to be normal to begin with, but this one is not normal to begin with. It says it's very skewed right. Well, if that's the case, then we want n to be larger than 30 in order to ensure the distribution is normal, based off of the notes from chapter 8, the central limit theorem in particular. And that's why we say here, to construct a confidence interval, the mean either, the distribution of the mean must be normal, but in order to obtain that, you have to have n greater than 30 or the population distributed. So we don't have the population distributed, so we have n greater than 30. And that's all they're writing up there. All right, so then in 2009, there were approximately 30,000 fatal crashes in which a driver had positive BAC. Explain why this, along with the fact that they were abused. Simple random sample satisfies the requirements. Okay, well, let me go back to look at the requirements again. So we now know in part A that n is 45 or 1,300, excuse me, which is greater than 30. So let me type that up. 1 second. Okay, there's the answer for part A. Since the population distribution was skewed right, we must have n greater than or equal to 30 in order to ensure the distribution of the sample mean is normal. The central limit theorem for x bar from section 8.1 is where we learned all of that. All right, so since our n is equal to 1,300, that is definitely much bigger than 30, and therefore the distribution of sample means, i.e. x bar, is normal. All right, then we were just talking about why is it we must have n equal to, was n equal? Yeah, 1,300. So let me just show that the other two conditions that we had, so other conditions for making a confidence interval are simple random sample of size n, and that little n must be greater than or less than or equal to 5% of capital N in order to ensure that the distribution is normal. All right, so let me write those in. Okay, so excuse me, in order to ensure independence, I apologize. The other condition, this part is to ensure normality. This part is normal. This part is going to be ensuring that it's independent. So we have this piece. So we have this piece given to us in the instructions in the setup of the problem. Okay. And then we need to prove that little n is less than or equal to 5% of capital N in order to show that the samples are independent. Little n less than or equal to 0.05 capital N question mark. All right, little n was 1,300. Okay, and then 0.05 capital N was, let me go back, 30,000. So I'm going to grab this 30,000. All right, let me grab the calculator. Clear this out. 0.05 times 30,000 is 1,500. So this is 1,300 is less than 1,500. Yay. Okay, so these are question marks. We're not sure at this point, right? We kind of don't know if it is. And then down here, we prove that it is. There we go. This will make it so that our samples are independent. Since 1,300 is less than 0.05 of capital N, the samples are considered independent, and therefore we can make a confidence interval. All right, great. I bet you part C is going to be make that confidence interval. So let's see. Let me go back and read it. Determine and interpret a 90% confidence interval for the mean BACs. All right, so let me type that up 1 second. All right, there we have it. So it's important to notice a couple things. You're making a confidence interval for the mean. They put it right here. We're talking about average. That means that you're using, from your inferential statistics sheet, this one right here. So if you had to do this on the test, you might have to do this by hand. So let me just show you all of this. And we'll use the calculator as well, don't worry. Calculator is very helpful. So the formula is x bar plus or minus t alpha over 2 times s over the square root of n. Let me just change these to bold so you can see it more clearly. All right, and then we're going to have to find all of our values. So x bar was given to us. This is the substitution step. When you're doing this by hand, you'll have to do this, and you might as well get used to writing it when you're doing your homework. So x bar was, they gave it to us in the problem, hold on, 0.19 over here. And while I'm on the subject, S is 0.09 and N is 1300. Let me write those up real quickly. There we have it. So X bar is 0.19 grams per deciliter, S equals 0.09 grams per deciliter. So I'm going to put 0.19 right here, 0.09 right here, N is 1300 right here. Now let's go figure out the degrees of freedom real quick. Degrees of freedom would be 1299, right? And while I'm on the subject, let's figure out alpha. The sea level is 90%, right? That means that alpha is 0.10. That means that alpha over 2, there we go, alpha over 2 is 0.05, okay? There, and I just popped in a quick visual for you so you could see. So the center is 90%, then 0.05 is over here, 0.05 is over here. And that means that we're going to want the T alpha over 2 would be T 0.05, comma 1299. To find that, we're going to need a calculator because 1299 is not in our tables. If I go to the T table, the closest I'm going to get is 1,000, which would be if I go 0.05, 1299 would be 1,000, 1.646. That's probably what I'm going to end up using, but let's see. So if I grab the calculator, I can use inverse T, 0. It doesn't really matter. Either 0.5 will work or 9.5 will work, but 1299 is your degrees of freedom. Yep, see 1.646. There we have it. So it didn't matter in this instance if you use the table or the calculator. It doesn't make any difference. You're going to get 1.646. Okay, so then, oops, we use that value here in the formula. So that's the part where you substitute right here and make it 1.646. Now, instead of typing all of that into a calculator, you can just write your result using the calculator to come up with it. Now, remember that on your inferential statistics sheet, it tells you which calculator instructions to use. So if I go here, I can see this is the one I'm doing, the one sample mean. So it says right there, use T interval. T interval on the calculator. So let me go to Stat, Tests. T interval is number 8. If you have an older 84, you won't see it on the first screen. You'll have to kind of scroll down to it with your down arrow, but it's number 8. You can just press 8. All right, now data, remember, is when we have a column of data, like we had raw data, but we didn't have that in this instance, so there's no way we're using data. So I'm going to move my cursor to Stats and press Enter. And I'm going to type in the numbers I have. I have an X bar of 0.19. I have an S of 0.09. And my N was 1300. And then I have a confidence level of 0.90. I'm going to go down to Calculate and press Enter. And there it finds it. So 0.18589 and 19491. or 19411, excuse me. There we go. There we have them all in there. And I just put the calculator so you could see it, but of course you don't actually have to do that. If you're working on an exam, you have to show these three parts. You have to show the formula, substitution, result. It'll help if you show these parts as well, especially this middle section here where you try to figure out what your alpha over 2 is and what your t-value is, because that's what you're going to need from your own brain in order to be able to substitute here in step 2. Okay, so then we have that. Let's just double check our answers real quick. So they say 186 and 194. And that matches what we have. We've just rounded it, 186 and 194. And you're done. And then let's see, what else do they want? All areas of the country use a BAC of 0.10 as a legal intoxication level. Is it possible that the mean BAC of all drivers involved in fatal accidents who are found to have test positive is less than the legal intoxication level? Okay, so 0.10, let's look back at our interval for a second. So our interval is from 0.185 to 0.194. And let me read the question again. They're asking, is it possible that the mean BAC of all drivers involved in fatal accidents who are found to have positive BAC values is less than the legal intoxication level? So what they're saying is it possible that it's less than what we had? And the answer is sure, it's possible. I mean, we're not 100% certain that the mean BAC level is in here. We just are 90% sure it's in there, which means there's a 10% chance that the true level is not in there. So let me type that up. There we go. So we are only 90% confident that the mean BAC level is between 0.186, and this is technically grams per deciliter, and 0.194 grams per deciliter. It is possible that the mean BAC of all drivers is less than 0.10 grams per deciliter, but it is highly unlikely. And that's because that number 0.10 is far below our confidence interval. We're 90% sure it's in here, but we don't think it's like super far away from here. Like if it was 0.18, you'd be like, okay, but 0.10 is really far away. All right, I think we are all done with this question. So let me just double check that real quick. Yep, we're all done. All right, so I hope that was helpful, and I'll see you back here for more